Today we're going to finish the lecture on Chapter 9. The beginning of Chapter 9, which we completed last Wednesday, finished up with the valence bond theory, which is supporting of the which is supported by the localized electron model. Now we want to introduce the topic of molecular orbitals, which is better suited to answer some of the questions that the localized electron model could not. So without any further discussion on that, let me see. Here we go. I'm going to open the PowerPoints. There we go. Let's make a slideshow out of it. Now, okay, this is where we paused. We had finished up with the localized electron model of the valence bond theory. And now we want to introduce the topic of molecular orbitals as a necessity to answer questions and repair limits to the localized electron model. What we've discovered over time and with other studies is that the localized electron model incorrectly assumes that electrons are localized. That is, they are assigned to either an individual atom as lone pairs, or they only reside in the space between the atoms, either on axis as a sigma bond or slightly off axis as a pi bond. So, and what that required us to do in many cases was to introduce the concept of resonance. In other words, you can have several valid Lewis dot structures, but you can't choose between them. I mean, they're all equally valid, and their formal charges on the atoms are as low as possible for two or more of the dot structures. So we had to introduce resonance as sort of a limited fix. Molecular orbital theory will take care of that without much effort. So these unpaired electrons, I mean, what are they doing in there? Well, of course, we assign them to individual atoms, but they're not there for no reason. Let's see, we got another attendee dropping in. 1, 2, 3, 4, 5. Okay. So these unpaired electrons, while we think of them in terms of just kind of sitting on the sidelines with the localized electron model, in the molecular orbital model, they are active participants in the bonding process. All right. Who did I miss? Oh, I didn't miss. No, scroll down, excuse me. Scroll down. There we go. Okay, that's everybody that is normally here. All right. The localized electron model also does not provide direct information about bond energies. Now we can infer bond energies from other experiments, but the model itself says nothing about the quantitative bond energies. How did I end up with? Go figure. I went backwards, I guess. So now we're going to look at the molecular orbital model. And the molecular orbital model actually takes the entire molecule, no matter how big it is, and that is your locus of operation. And the orbitals that are developed in the bonded molecule are assigned to the entire molecule. In other words, they don't belong to any one person. It's kind of like communism for chemistry. So this collection of nuclei and electrons redistribute the electrons in new orbitals. They're not just overlapping atomic orbitals. These are entirely new orbitals that are that extend over the entire molecule. Thus the name, molecular orbitals. So this is a brief comparison of the characteristics, either localized electron model on the left, molecular orbital model on the right. The obvious difference is that the LEM relies on atomic orbitals only, whereas the molecular orbital creates these new set of orbitals called molecular orbitals. What the quantum mechanical, remember when we were doing electron configurations for each element, and we would draw the orbitals and how many electrons were each, like 1s2, 2s2, 2p6, so forth and so on. What the localized electron models was, it just took those orbitals and used that quantum mechanical definition extended to molecules. With the molecular orbital, an entirely new approach to the development of those orbitals is invoked. And while the molecular orbitals are built from existing atomic orbitals, they're entirely new, and they have their own quantum mechanical definitions. All right, while we assume that the electrons are localized to atoms and between atoms in the bonds for the localized electron model, for the molecular orbital model, these electrons are delocalized across the entire molecule. So that being said, it's kind of hard to think of them in terms of particles, because, you know, how do you smear a particle over an entire molecule? Well, we're going to deal with it. The one thing that they do have in common is, for each of the molecular orbitals, you still only can have 2 electrons, like spin up, spin down, similar to the localized electron model. And the wave function approach, the psi squared, which is used to define the probabilities of finding an electron in a given area, I should say volume of space. That same approach is used for molecular orbitals, and the energy is quantized. That is, the electrons don't move one level to the next unless they also either absorb or emit energy of a certain wavelength or frequency. There's nothing, no in-betweens. It's quantized. It comes in packets. So that is still common to both the molecular orbital and the localized electron model, except that we have to use different formulas to calculate the psi square for the molecular orbitals. But the concept is still there and the same. One thing that we do is that when atoms come together, they have a certain number of atomic orbitals, and this is right down to the nucleus, all of them, not just the valence orbitals. all of the atomic orbitals are reconfigured as molecular orbitals, and the number of molecular orbitals that you end up with after that configuration is the same number that you started with. So if you have two atoms and they have 5 orbitals each, when they become a molecule, you will have 10 molecular orbitals. So that is conserved. The number of orbitals is conserved. So the way we get around that, the way that we approach the reconstruction of the atomic orbitals is the concept of bonding versus anti-bonding orbitals. And I'll show you that in a, I think in a chart here in a second. It comes too late. Let me do it now. So if you have, well, let's just use an example, say hydrogen. So here's your energy bar, right? And you've got a hydrogen atom here, you got a hydrogen atom there. Okay, this hydrogen atom has a 1s orbital, and this one has a 1s orbital. So this is the H2 molecule in between. So in here, we're going to show the molecular orbitals that are derived from these two atomic orbitals. What we do is when we mix them together, we get one here at higher energy and one here at lower energy. This would be the bonding orbital. This would be the anti-bonding. Sometimes we draw little dashed lines to show the origins. Okay? So this is going to be, maybe that's as far as I need to go right now. We got one electron here, one electron there. And also, you fill the orbitals the same way you do with atomic orbitals. You start with the lowest energy and you work your way up. So these two electrons go down here in the bonding orbital. And there's nothing going into the anti-bonding orbital. This particular one is a 1s, actually a 1s sigma. And this is a 1s sigma star. We always put a star on the anti-bonding ones just as a convenient way to tell them apart. But we identify the sigmas because that's kind of a holdover from the valence bond theory. The sigma bond is on axis still, if you can think of it in those terms. And if we had an opportunity to build another bond beyond this one, it would be a pi. Until you get to the next level. Right? So that's all I'm going to say right now. We'll fill in the blanks as we go. We still call it a sigma molecular orbital. Right? Atomic orbitals don't exist anymore. Right? Here's the molecule. These guys are history. They only serve to provide the logic for developing these molecular orbitals. So here's your first video.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So constructive and destructive interference never occur at the same time. Instead, they alternate one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. But check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right. Typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
All right, so this concept of interference is important for furthering our molecular orbital understanding, simply because electrons can either be considered particles or waves. As particles, they don't give us much information as far as bonding goes. They can be viewed that way when they're independent particles, like particle beams or something like that. But when bonding is required, the concept of constructive and destructive interference is much more valuable. So when you think of the bonding and anti-bonding orbitals, think of the bonding orbitals as constructive interference and the anti-bonding as destructive interference, because we can describe electrons as waves. Now, one word that was not mentioned in this video was superposition. He didn't use the word, he just described the process, where two overlapping waves are the summation of the heights at that particular point where they overlap. That's the superposition. He did mention interference. And interference, we have to sort of modify our thinking when we talk about interference in terms of wave behavior, because interference generally has a negative connotation. But in the sciences, interference can either be constructive, which we would normally associate with positive, and destructive interference we'd associate with a negative emotion. But interference stands alone as an unemotional description of wave interaction. All right, we mentioned these before, constructive and destructive interference. Now, the waves that were shown in that video were of the same frequency and wavelength, so it was easier to visualize them. But interacting waves don't have to be the same. When they interact, they can form very complex patterns. In fact, the interacting of waveforms across copper wires is the way we transmit information. The way information is being transmitted right now across our internet connections. And what that involves is oh, my mind's gone blank again. It'll come to me later. When those waves interact, they can form complex patterns that can be decoded on the other end. In other words, you have a carrier wave like that, and then if you superimpose other waveforms on it, they can look weird like that. But electronically, you can extract, say we superimpose something else like that on this wave. On the other end, I just remembered the word. It's called multiplexing. You can extract that information from this combined wave simply by electronically imposing destructive interference and removing that waveform. So if you remove that waveform by destructive interference, then you're left with this waveform, and that's where your information is. The simplest way is AM radio, which is amplitude modulation. And that was the first form of communication, was that amplitude modulation in either AM radio or in shortwave radio or whatever it happens to be. But the electronics in those days was such that that's all they could get away with. Then came along FM, which is frequency modulation. And now over the wires, they can superimpose multiple signals on the carrier wave. So that's how that's one of the ways they pack a lot of information into a single signal. Now, of course, there's so much information that's required to be transmitted, especially with video, that instead of having just one of these, they have what they call broadband, which means you've got several carriers of different frequencies going across that wave at the same time. And then at the other end, you have to separate the carriers, and then you can decode the carriers and reconstruct them on the other end. It's pretty complicated. Anyway, so let me get back to the topic here. We can think of the atomic orbitals in the process of forming our molecular orbitals is an example of constructive and destructive interference. So here's your hydrogen atoms. Here's the s orbital from one of them and the s orbital from the other one. And this is a very simplified version. The mathematics is much more complicated. But if you invoke destructive interference, you get an antibonding orbital with very little electron density predicted between the atoms. Whereas with a bonding orbital, where you have constructive interference, you have a large amount of electron density in this molecular orbital between the atoms. So this would be the sigma bonding, this would be the sigma antibonding. Okay, and I showed you that diagram before with the energies. When you combine these atomic orbitals, the bonding orbital generally has a decreased energy level, and the antibonding has an increased energy level. And remember, I've always said that the lower the energy, the more stable the system. And when we're talking about bonds, it means a more stable molecule and a stronger bond, the lower energy you can obtain. Okay, so here's the picture I drew earlier. There's the hydrogen atom 1, hydrogen atom 2, and then you combine to make the molecular orbitals. So here's your antibonding. It's got nothing in it. There's the molecular orbital that's bonding, has both of the electrons in it. Now, the way we're going to use bonding and antibonding orbitals is to determine whether or not the bond can actually occur, or if it does, how strong it is. We can make a qualitative prediction using that information. What's the confirmation for the molecular orbital model? I mean, if the model doesn't explain and predict accurately, then it's not worth anything. So one thing that the molecular orbital does is it describes electron distributions and their energies that agree with all the previous ideas that we've had about bonding. Also, the labels that we place on these molecular orbitals have something to say about their shape, which is derived from the parent atomic orbitals, whether they're bonding or antibonding. Now, they're not exactly identical, of course, but we can see their parentage. In other words, the molecular orbitals sort of carry some genetic code from the atomic orbitals. We can write the electronic configurations in a similar fashion to the atomic electron configurations using those molecular orbital designations like the 1s sigma. There's a 2s sigma, there's 2p, 2p sigmas also, and 2p pi's. But we can write those out in a shorthand way, just string them out like that. And you can get an idea from that without having to draw the big diagram, something about the molecule itself and the structure of its orbitals. And we repeat, the number of orbitals are conserved. Okay, so how do we make use of this information? Well, suppose we have a molecule in which we have inserted electrons into bonding and anti-bonding orbitals. So we've got all of our electrons that we started with, all the orbitals that we started with, we produced molecular orbitals, and then all the electrons go in there, stacking from the bottom up. If you want to know something about the bond strength, then all you have to do is add up all the bonding electrons, those electrons that we placed in the bonding orbitals, and subtract the ones that we placed in the anti-bonding orbital, and then divide by 2. And that gives you a number we call bond order. The bond order, the higher the bond order, the stronger the bond. Sometimes the bond order pops out as whole number integers. Like it may come out as a 1 or a 2 or even a 3 or even higher. And we can draw some qualitative parallels. Generally speaking, if the bond order is 1, that signifies a single bond. If the bond order is 2, double bond. Bond order 3, triple bond. So we would expect if we drew the, and we'll do that actually, if we drew the molecular orbital diagram for dinitrogen, the way we would draw it with our Lewis dot structure would be like this, like that. And we would expect to see a bond order of 3 for that molecule. And in fact, we do. So it's a very strong bond. That being said, the bond order doesn't have to be whole numbers. I mean, you frequently come up with fractions. Particularly 1/2 appears a lot, simply because of that 2 right there. If the difference up here is 3, then 3/2 would be 1.5 bond order. So it'd be somewhere in between here and here. Now, the valence bond theory never does that. It just says it's either a single, double, or triple, period. And then if you have any leftover electrons, they just sort of sit out there as lone pairs. But the bond order takes into account every electron in the molecule. All right, so here's the designation. I put 1s in the wrong place. This is sigma 1s, and this is sigma 1s star for the anti-bonding. And if we calculate the bond order, 2 minus 0 divided by 2 is 1. So hydrogen you would expect to have a single bond, and it does. Now that's for the neutral H2 molecule. What if you add an electron? Where's that electron going? The only place the extra electron can go is in the anti-bonding orbital. Right? So if we calculate the bond order now, we get 2 minus 1 divided by 2 is 1/2. So what have we done by adding an electron to a dihydrogen molecule? We have weakened the bond. We've gone from 1 to 1/2. So the molecule does exist because it has a non-zero value here, but it is weaker than the H2 neutral molecule. Let's see, I thought we were going to take one away. That's okay. Let's watch one more video. Let's see. I'm catching up with my hard copy. Okay, so here's going to be a general description and discussion of molecular orbital theory.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have 2 isolated hydrogen atoms. And we know that each isolated hydrogen atom should have 1 electron located in the 1s subshell when in its ground state. And of course, we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when 2 atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those 2 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the 2 hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these 2 nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have 1 more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the 2 nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the two atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these two atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these two different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed two new molecular orbitals from our two atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, one from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have 2 more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding. So 2 helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibodies, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find: a molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second-row element, nitrogen. Nitrogen also has 2 p atomic orbitals available, but in this case, only 3 electrons in each. So let's combine those and form a new molecular orbital system. And you might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see: a diatomic molecule with a triple bond. Now let's consider one more element in the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, but not enough to completely counteract all of those bonding electrons. So there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching.
Okay. That was a lot more information than you probably wanted to see at one time, but that was a good discussion. One thing that you may have noticed is the speaker left out the 1s and the 2s derived molecular orbitals. As far as it goes, now they're there, right? It was just more convenient to leave them out, simply because the molecular orbitals derived from the 1s and the 2s electrons for fluorine, for instance, all of the bonding and anti-bonding orbitals are used up, right? There's really no variability there. So when you do the bond order calculation, they're a wash anyway, right? The bonding and the anti-bonding, they're going to cancel out completely. So you can get the same bond order calculation from just using what we would normally consider valence electrons. Nitrogen, like the man said, is extremely stable. And that's why it's used in packaging, like your potato chips now. When I was growing up, preservation of potato chips was almost impossible. In other words, they would go rancid over a period of time or go stale because the oxygen that was in the bag packaged with them would react with the oils and the various components and produce off flavors, and you'd lose that crisp. Well, the first thing they tried was used antioxidants. Now, they actually put chemicals in the potato chips that would consume the oxygen. And it worked. But you were eating those chemicals too. So then they moved those chemicals into the packaging material so that they wouldn't be directly mixed in with your potato chips. So they'd be in the packaging material and they would still consume the oxygen. Things like BHA and BHT. But that fell into disfavor as well. So they moved to packaging the chips with an inert atmosphere. And nitrogen was perfect for that. Nitrogen will not react with your potato chips, and it excludes all other oxidizing elements like oxygen. And the other benefit is nitrogen, pure nitrogen, is cheap. It's dirt cheap. All it takes is just a little bit of energy to extract nitrogen from the air, which is 78% nitrogen to begin with, and you got all the nitrogen you need. So once you open the bag and expose it to oxygen, then you start the oxidizing process. Okay, let's see. There was also a mention of paramagnetism. We're going to cover that in just a minute. Okay, the types of molecules that were being described in that video are homonuclear diatomic molecules. They are the simplest molecules that we can use to introduce you to the concept of molecular orbitals. When you start getting into heteronuclear molecules, where you have maybe nitrogen on one side and oxygen on the other, coming together to form a bond. Then things get a little squirrely because the original energy levels of the nitrogen and oxygen are different. So when they come together, I mean, how do you resolve that difference into a molecular orbital format? Well, it's mathematical. And we can't go into that too much depth in this class. So we're gonna confine our discussions primarily to homonuclear diatomic molecules. And like this statement says, when we draw the diagram, unless explicitly commanded to include every orbital from the atomic level into the molecular, you would just use the valence orbitals to discuss the formation of the bonds. Okay, so paramagnetism. Paramagnetism is a phenomenon that's observed in some elements, some compounds too, in which the compound is attracted to a magnetic field. Now, the way it does that is once those electrons start to experience that electronic field, if you have paired electrons, then the magnetic field is going to induce a secondary magnetic field in those electrons. So if you've got one up and one down, they cancel each other out. So there's no induced magnetic field for those electrons. But if you have unpaired electrons, they do produce individually induced magnetic fields, and they actually strengthen one another. So that's what we saw with oxygen. We have those two unpaired electrons, and that induced magnetic field interacts with the external magnetic field and attracts one to the other. So you may have, well, I don't know if you've seen it. I don't have a video for it right now, but your book may have a picture. You've seen these huge horseshoe magnets, right? They're shaped like right? And you'll have a North Pole and a South Pole. And the magnetic field in here is extremely strong. So if you pour liquid oxygen into that gap, within the limits of the size of the gap, it'll all stay right there in that gap as long as it's liquid. Once it turns into gas, then it has the opportunity to develop a vapor pressure and blows off. But as long as it's liquid, it'll stay right there in that gap because of paramagnetism. The opposite of that, or the converse, I should say, is diamagnetism. Diamagnetic compounds are actually repelled from that external magnetic field. And nitrogen, dinitrogen is a perfect example. All of its electrons are paired. So there's no attractive force whatsoever. You pour a liquid nitrogen in there, it goes straight through. No interaction whatsoever. Now this phenomenon can be quantified. You can put actual numbers. All you have to do is have the right equipment. And this is an example. This is sort of a schematic. All you have is your sample, and you lower your sample into the magnetic field, and you can measure with this very sensitive balance whether the sample is being pulled into the field or it's being repelled. And you would probably form you probably have a graph. So if you had this x-axis would be distance, and this would be force measured. Then if you have a paramagnetic element, in that sample tube, then as you get closer and closer, coming back this way, closer to the magnetic field, you would see a force jump up like that. And you could measure it. So this phenomenon, diamagnetism and paramagnetism, there was no hope whatsoever that the valence bond theory would ever explain that. It had no capacity to explain these phenomenon. And that's one of the problems that the molecular orbital theory corrected. It's able to explain why this happens. Okay, we got Professor Dave. He's got his hair cut off this time. I don't know whether this is before or after the last molecule. I think he probably has got it cut off in his elder years. But let's see, this one, well, it's 9 minutes long. It's worth it. So let's sit back and relax.
It's Professor Dave. Let's revisit molecular orbital theory. He knows a lot about the science stuff that Professor Dave explains. We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior, in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the antibonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and antibonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of 2 atomic orbitals will always result in 2 molecular orbitals, one bonding and the other antibonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with 2 1s orbitals combining to form 1 sigma s orbital and 1 sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put 1 electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 anti-bonding electrons, including the sigma 1s star anti-bonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have 2 unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital. But on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay.
It's Professor Dave.
Oops,
Let's
sorry.
revisit molecular orbital theory.
There we go. So this looks almost exactly like the diagram he was showing to describe sp mixing. He was correct about one thing. When you add up the bonding and when you calculate your bond order for neutral diatomic atoms, homonuclear diatomic atoms, molecules, the calculation of the bond order doesn't change, doesn't affect that. It only is affected if you try to calculate the bond order for modifications to these, such as adding electrons or subtracting electrons. When you do that, then the electrons are removed or added to the highest energy levels. And if you're adding electrons to an antibonding order, that weakens the molecule. If you're adding them to a bonding orbital, that strengthens the molecule. Conversely, if you have a neutral diatomic atom molecule and you subtract electrons from the antibonding orbital to make the ion, the cation in this case, then you strengthen the molecule. Whereas if you subtract them from a bonding orbital, then you weaken the molecule. So when that happens, then it does matter what order things are in. All right. So you'll notice that generally speaking, dioxygen, difluorine, I don't even know why they put dineon in here because it's unlikely to exist. But oxygen and fluorine are over here to the right of this breaking line. And notice now that the sigma's on the bottom and the sigma star's on the top, and both of the pi's are in the middle. That's an indication of insignificant sp mixing. Whereas on the left, from nitrogen to the left, the dinitrogen to the left, you do get significant sp mixing, and the pi and the sigma flip. Now we got the sigma above the pi. Notice we got 2 pi's here and 2 pi's there. Well, 2 pi antibonding here and 2 pi bonding here. And what we would normally expect is that the sigma would be lower than that, but with the sp mixing, now the sigma is higher in energy than these pi's. Okay, so that's a way to generalize this graph. Here's another way. In this case, we don't just show the orbitals. We show the electrons that are used to fill the orbitals. And with that being said, notice that all of these for difluorine are paired. All but 2 of the oxygen electrons are paired. These 2 are unpaired, which leads to paramagnetism rather than the fluorine's case, which is diamagnetism. You get diamagnetism for nitrogen and for carbon because you've got all paired electrons. But when you get to boron, you find that these electrons are unpaired. And notice that the what we have done, let's see, let's see, 2p. Okay. So these sigmas that are formed from the s orbitals, the 2s bonding and antibonding, they don't flip. It's only when you have interaction in the p orbitals between pi's and sigmas. And in that case, we see that here's the sigma above the pi, and over here, the sigma is below the pi. So with no mixing, the pi bonding and antibonding are together in the middle. But with mixing, they're separated. You still have the sigmas on the high end and the bonding orbitals below, but they're flipped for sp mixing. Okay, and this also shows you the bond order, and it gives you the observed bonding energies and the bond lengths. So you find that the higher the bond order, the stronger the bond, and the length of the bond decreases. Also, the energy of the bonds increases. Okay, so that hasn't changed. That's experimental data. Regardless of what theory you're using, that's still there. It just helps confirm that your molecular orbital theory is on track. All right. That's true. Sigma pi mixing instead of sp, which is probably more accurate. The sigma and pi actually mix as molecular orbitals, not the s orbitals and the p orbitals mixing, but that's semantic as far as we're concerned. It may have some value for physical chemists that study this stuff, and it may have a bearing on their calculations, but for our purposes, 6 of one, half a dozen of the other. All right, so here's an example of a heteronuclear diatomic molecule. In this case, we have carbon and oxygen, carbon monoxide, one carbon and one oxygen. And I pointed this out, I extracted this diagram. I can't remember if it's from the textbook or from a previous slide or whatever. But whoever created the slide made an error here. This should be 2s, corresponding to this 2s. So notice that the energy levels for the carbon atom are higher. And that's consistent with our periodic trends that we've learned before. As you move to the right, you increase the effective nuclear charge, which tends to shrink the atom, and the orbitals now are moved closer to the atom, which means lower energy. So oxygen is going to be starting off with lower atomic orbital energies than carbon is, and that will influence the the constructive and destructive interference calculations that lead to molecular orbitals. But in this case, we're only talking about the second period, the 2s and the 2p. And we find that we get actually more significant differences than you would expect otherwise. Let's see, we have the sigma s, and here we have, and where's the sigma s star? Up here. So we have a pi here and sigma here, so it looks like there is mixing there, which we wouldn't have expected, except that carbon the dicarbons experience mixing, whereas the dioxygens, no mixing. So what happens when you put them together? It depends on where the relationship of their orbitals are. I mean, how are they in energy relations? And it turns out that the influence of carbon, in this case, causes mixing in the CO molecule, right? You would expect this sigma star to be down below the pi's if there were no mixing. But in this case, it is above. Okay, that won't change the paramagnetism or the diamagnetism because these are all paired here and these are all paired here. If you put them in either way, you're going to end up with all paired electrons. And it won't change the calculation of bond order either, not for the neutral molecule. Okay. One thing we might point out is that carbon monoxide is isoelectronic with dinitrogen. So you should get a bond order of 3. I wonder if that's true. Let's see, how many we got here? Bonding is 2, 4, 6, 8 minus 2 divided by 2 equals 3. So you do have a bond order of 3 for carbon monoxide, and there should be a triple bond in there, based upon our previous definitions of single, double, and triple bonds. Okay, let's see. Still have a little ground to cover. How about HF? HF is even weirder because hydrogen only has a 1s orbital. So how do you get molecular orbitals out of a 1s and the orbitals for fluorine? Well, as it turns out, the 2p orbital of fluorine is lower in energy than the 1s for hydrogen because fluorine has a higher effective nuclear charge than hydrogen does. But the electrons still prefer to be closer to the fluorine atom. It is electronegative, so that hasn't changed. So let's see what that looks like in terms of an energy diagram. So here's your hydrogen at this high 1s orbital level, mixing, or I shouldn't say mixing because that confuses, combining, interfering in such a way as to produce a sigma and a sigma star. So this 2p orbital down here combines with this 1s to give you a sigma molecular orbital and a sigma star molecular orbital. And with one electron in this p, right, fluorine actually has 5 electrons in p's. So we're only using one of the p orbitals here. Right, the other two we can effectively ignore. But when you combine this one with that one, you get this arrangement where this one is just a little bit higher than that one, but this one is a lot lower than that one and just a little lower than this one. But what is the bond order? It's 1. It's still 1. Same as if it were difluorine. 2 divided by 2 is 1. It also predicts that this should be a stable molecule, and in fact it is. And that difference in energy, right down here, is sufficient to stabilize the molecule. This is artist's rendition. You would expect to see the electron density slightly shifted toward the fluorine atom. And if we look at the model here, right, those electrons are closer to the energy of the fluorine than they were to the hydrogen. right? So this electron dropped way down in energy. This one only dropped a little bit. And that drop is another indication that fluorine is the stronger attractor. All right. Let's see. All right, we're saying stuff here that's already been said, and it works for either the valence bond theory or for the molecular orbital theory. It still predicts polarity, leaning toward the fluorine, right? So that's good. I mean, we've introduced a new theory, but it sort of incorporates all the good parts of the old theory plus more. All right. What is delocalization? Well, we've really kind of partially discussed it already when we said that atomic orbitals are reconfigured into molecular orbitals, and the molecular orbitals effectively redistribute electrons over the entire molecule. That, in effect, is a delocalization, right? They're not localized on an atom anymore. But when we think of delocalization, it's more appropriate to define it in terms of the pi bonding rather than the sigma, because even with molecular orbitals, the prediction is that the sigma bonding electrons will have more electron density between individual atoms. And the opportunity for more delocalization arises with the pi bonding electrons. So this is sort of a hybrid, so to speak, of the two theories, localized electron and molecular orbital models. And benzene is a perfect example. If we describe benzene in terms of single and double bonds, as we would with the localized electron model, then we would have to draw two equivalent structures. Here, the double bond is, say, on that axis, and there it's gone. It's moved over here. And when you do that, you got to shift all around. And you'll quickly realize that there are really only two structures that need to have resonance. So this model is the resonance model for benzene. And this is also the localized electron model, right? Because we are overlapping atomic orbitals. In fact, these are hybrid orbitals, sp2s. And what does that leave us? That leaves us with one p orbital that's unused. And that p orbital is the one that overlaps and causes the delocalization of electrons in the space above and below the ring, that ring structure. Another way to look at it is like this. See, those are your p orbitals that are not used, they're not hybridized, and they delocalize the electron density around the molecule. And that's one way to look at the increasing stability that is associated with benzene. Is because of this delocalization. Now we're getting closer to the molecular orbital theory when we do this, right? With the localized electron model, there was no way that you could depict this in a Lewis dot structure. But with the molecular orbital model, it's easy. Okay, let's see, we got a couple more. Oh, I left this one in here. This one's not going to show because it's written in that language that's not supported anymore. So we'll just skip over that one. I could say that the delocalization of electrons is not just for benzene. It works for a whole host of neutral and ionic structures. This last slide, I used to just dismiss this one entirely, but the photoelectron spectroscopy is an analytical method that confirms the molecular orbital theory. And with it, you can determine the relative energies of your electrons, either in individual atoms or in molecules. So the short version of how it works is we direct high energy photons at the sample, and then the kinetic energy of the electrons is measured. Right? So the amount of energy from that photon that is absorbed by the electron liberates it. Think in terms of, let's see, I started a sentence that I can't complete. The photoelectric effect for metals. So if you direct at a metal, if you direct energy at that metal, if it's above a certain threshold energy, it will eject an electron. It's got enough energy to do that. So that electron will sit right there at the surface if you reach the minimum amount of energy. If you exceed that amount, then the extra energy is transferred into that electron as kinetic energy, mass with a velocity. That's what this system measures. They measure the electron energy, electron energies in the molecule by the energies of the ejected electrons. And then by some calculation, they determine what the energy levels are for the electrons. Now, high energy means that you don't just eject these first two. If it's high enough, you can just keep ejecting all the way down through series of molecular orbitals. And with the calculations of those energies agreeing with the experimental data, that's just another way that we confirm that the molecular orbital theory is valid. All right, I think that's the last slide on this topic. And we finished chapter 9. So now you need to dig into your homework and your review documents so that next Monday we can come back and work some problems, review, settle any issues you have in time for the exam, which will be, let's see, should be the week after that. Right, we just finished part 2. We have a review on Wednesday, excuse me. Yeah, review on Wednesday, I'm sorry. We'll come back Wednesday review, and then the next Monday, the 26th, will be that exam. And then we'll follow up with however much review you need. We have Wednesday the 28th, Monday the 3rd of May is available as regular class time, and then we go into final exam week. And let's see, actually, May the 5th, I just left it off, right? That could be a free day. We don't go into final exam week until the 10th of May. So if we get all our review done for on Wednesday and Monday of the following week, then you can have an extra day off, and you can use it for chemistry, use it for whatever you want. But that's what we're looking at. We're coming down the home stretch. And then we'll have a comprehensive final.